Hello. Today we're going to prove De Morgan's laws. Actually, only the first one. The second one is left as an exercise. Here, A, B, C are all sets. The first one says A minus the union of B and C equals to the intersection of A minus B and A minus C. So this is a fairly typical proof in set theory. So before we actually get on with the proof, there's a few definitions we need to look up. This was the main point I was trying to make in my exercise video. Before you actually start with any questions, you first have to understand the question. And here we see a bunch of operations that are denoted as minus, this union symbol, this intersection symbol, and we also have the equal symbol. So the first thing we do is to look up the definitions. I'm using the definitions given in Moncrief's book on topology, but I'm pretty sure all math books use the same definitions for these set operations. All right, first we have the set difference. So A minus B is the set of X that is in A but is not in B. So here is a visualization using Venn diagram. A minus B is always going to be a subset of A. Essentially, the set difference between A and B is the part of A that is not covered by B, intuitively speaking. Next up, intersection. So the intersection of A and B is the collection of X such that X is in A and X in B. So on a Venn diagram, it's this overlapping region. Next up, we have union. The union of A and B is the collection of all elements X, such as X is in A or X is in B. Bear in mind, in mathematics, the word or refers to at least one of these statements is true. And lastly, we have the definition for equality between sets. A equals B means A is contained in B and B is contained in A. And here we have the visualizations for containment. A is contained in B means if an element X is in A, then it must also be in B. All right, so let's actually get on with the proof. So here we're asked to show the two sets are equal. So let's use a double containment strategy. So let's first start from the forward direction. So I write a containment symbol to indicate that this part of the proof shows that the left-hand side is a subset of the right-hand side. So let's get started. So let X be an element in A minus B union C. So by definition of minus, X is in A, but is not in B union C. So now let's analyze further to see what this statement means. If X is not in B union C, that means X cannot be in either of them. So by definition of union, X is not in B and X is not in C. So far we got X is in A, but X is not in B, and X is not in C. So we can combine the fact that X is in A but is not in B to conclude that X must be in A minus B. And also we can use the fact that X is in A but X is not in C to show that X is in A minus C. So here X belongs to A minus B and A minus C simultaneously. X must be in the intersection of those two sets. And that's exactly what we needed, as needed. Right, so now we're done with proving the forward direction. Let's check the other direction, for which I need to pick an arbitrary element from the right-hand side, which is A minus B intersect with A minus C. Therefore, we write, let X belongs to A minus B intersect with A minus C. So we see that X is in the intersection of those two sets. By the definition of intersection, we know that X belongs to both A minus B and A minus C. So now we see that X is in A minus B and X is in A minus C. So let's apply the definition of set difference. By the definition of minus, X is in A, but X is not in B. And similarly, we have X is in A, but X is not in C. But because we already have written X is in A once, there's no need to write it twice. So we just write X is not in C. So we see that X is in neither B nor C. That means X cannot be in the union of B and C. But at the same time, X is in A. So that means X is in a set difference between A minus B union C, as needed. So now we've proved both directions. The set equality is now established. So we write a concluding sentence at the end to reiterate what we proved. So it goes like, therefore, A minus B union C equals to A minus B intersecting A minus C. And we usually use a square symbol to indicate the end of a proof. So that's it. I proved one of the two De Morgan's laws in this video. The techniques used for proving the second identity is also very similar, so it's left as an exercise. Let me know if you enjoy this type of content on elementary proof techniques. Thank you very much for watching, and I'll see you next time. Bye.